Hello everyone, welcome to a fresh new lecture on the topic Introduction to Signal Processing Architectures. This is Dr. Anirban Dasgupta and let's get started. So what do you mean by a signal processing architecture? So in general, what do you mean by an architecture? Suppose you are designing a building. So what do you mean by the architecture of the building? It means that how many bedrooms will be there, how many kitchen, or not only how many bedrooms and kitchen or how many bathrooms, but exactly where will you like to have the bedrooms or the bathrooms or the kitchen, and what should be the size of each bedroom and kitchen and the hall room, etc. Similarly, signal processing architecture typically refers to the structural organization of both the hardware and the software systems to process the signals. And why do you need an architecture? You can just plug in anything and will it not work? That might work, but like in a room, so if you keep anywhere the bedroom of any size and anywhere the kitchen, that will or might work, but you should have a better design for optimal usage. Similarly, in signal processing architecture, you should have these elements organized such that it is optimized for tasks such as filtering, compression, enhancement, and any analysis of signals, which are basically the different signal processing tasks. And this is important in building efficient. So what do you mean by efficient? Maybe efficient in terms of cost or space, and scalable, which means that once you make this architecture, you can repeat this process and make multiple copies of the signal processor. One example is the video which is recorded is using some architecture which is efficient for compressing the video, so that you get the best quality video with optimal use of resources or say minimum cost. So typically these are the components in a signal processing system, and it starts with sensors which converts the physical quantity to the signal or electrical quantity. That electrical quantity is conditioned. Conditioned means that this sensor can produce a signal which is either a current or a voltage. Now you cannot directly send this to an ADC. ADC takes voltage. So if it's a current signal, then you have to convert this current to voltage using some I to V converter like an op-amp. Then this value of the voltage may be in microvolts or in millivolts, but this ADC may accept something like 3.3 volts or 5 volt range. So if you send this level, then everything will be logic 0. So you have to amplify the signal. Also there can be some criteria for Nyquist sampling. So you need to have some anti-aliasing filter. So all these are performed using signal conditioning, which are typically using some analog circuits. Now once we get the signal ready or the conditioned signal, that is sent to my ADC. Now this ADC can be outside the signal processor or it can be part of the signal processor, and this converts the analog signal to my digital signal stream. Now this is processed. Process means it can be anything like filtering, compression, enhancement, whatever you feel like, and then the data can be stored in the memory. You can directly send the data from ADC to memory using something called direct memory access, bypassing the processor, or you can use the stored result to the memory. Like when my video is getting recorded, it is processed and stored, like compressed and stored in the memory. Or you can transmit to a digital to analog converter, which will convert it to real world analog signal, and then this actuator will convert this analog signal, which is an electrical quantity, to any physical quantity or maybe taking some physical action. Like one example is the speaker, or it can be a robotic arm. So there are several types of signal processing architectures. The first is a centralized architecture, which means there is only one system which is doing the signal processing task. Of course, this is burdened with everything because it is only doing the task, So, this is typically used when the complexity of the algorithm is low, like for example, basic filtering or convolution. When the complexity increases or the signal length is very large, then you can go for distributed architecture, where there are several processing units and they are working maybe in parallel or maybe in serial, but they divide the work like a divide and conquer approach. And parallel architecture, now parallel architecture can be centralized or distributed, but the main aim is that it can use multiple processing units that will operate simultaneously, and these are built using multi-core processors, graphics processing unit. Now GPUs are becoming very popular with the increase in deep learning algorithms. Then FPGA, these are field programmable gate arrays. I will explain what is this. So, you can divide a big task into smaller tasks which can be executed in parallel, and some examples are single instruction multiple data, where say one instruction like convolution can be applied to multiple data in parallel, or multiple instruction multiple data MIMD. Another example is pipelined architecture, where your processing will be serial, but your task will be divided into several stages and it will be occurring in overlapped fashion. It means that when one instruction is being executed by stage 1, the other instruction can use stage 2. And finally, the hybrid architecture, which combines everything. It can have centralized ability, it can have distributed ability, it can have parallel ability, it can also have pipelined ability and everything, and it can be used in extremely complex tasks that can use cloud system, cloud computing based signal processing, or even advanced communication systems. So, these are the typical types of signal processing architectures. Now, what are the signal processing components? So, this diagram I had showed you in the beginning, where I defined what are sensors, that it will capture the real world signal, and that is any signal will appear in the form of any physical quantity, and it will be an electrical quantity at the output of the sensor, typically a current or a voltage. Then signal conditioning is modifying the analog signal to have a voltage and frequency range which is suitable for digital conversion, and that is sent to my ADC, which will generate my digital signal, and this digital signal is processed using the digital signal processor, and it need not be a digital signal processor strictly, but here we are focusing on a digital signal processor. But nowadays people can use anything like microcontroller, microprocessor, FPGA boards, anything. Then memory. Now, whenever you are doing this processing, like if I ask you to solve a problem like 19 plus 3 into 7 plus 17, and it is very difficult to calculate directly by listening to the problem, you might prefer to write it down in some notes. So, that is the use of memory for storing the variables which I said, and for storing say intermediate results, used for buffering, like when the signal stream is coming, say for example, the signal is coming say 100 samples per second, but I am able to process only 80 samples. So, the remaining 20 will be kept in some buffer. Then digital to analog conversion, that is finally the output of the signal processor will be a digital signal y of n. So, that needs to be converted to analog for reuse, but then again this is an optional part, but many signal processing systems have this digital to analog converters. And finally, the actuators which can perform certain actions based on the output signal, and that can be as simple as glowing an LED or sounding something in the speaker, like say I want to have an alarm that if there is an anomaly detected, then it should sound an alarm that yes, there is some anomaly. So, that is an actuator. So, we will start with sensors. And I will not go in detail about sensors because this is not a sensors topic, but in general today all the sensors which are available or what you can see on the screen, they are compatible with many microcontroller boards like Arduino or ESP, as well as in signal processing boards, and most of them are digital sensors. So, they have the signal conditioning and the ADC inbuilt in the sensor itself. In some cases where this ADC can be separate, so you have to either implement a separate ADC for interfacing, or you can directly integrate to a DSP or a processing unit which has an ADC with it. And that is the next topic, which is analog to digital converters. So, ADC has typically 3 stages: sampling, quantization and encoding, and that is very easy to remember. So, what is sampling? Sampling is, we have the signal and we have explained. So, this is the signal analog in time, and this is say a voltage varying with time. So, sampling is discretizing the time axis, and this is typically done at a fixed rate. There are some samplers, or I would say ADCs, which can do non-uniform sampling, but for simplicity let us assume that it is a uniform sampling system, and this is specified by the sampling rate or sampling frequency given in hertz. The next is quantization, and quantization is discretizing the y axis or the amplitude axis. So, quantization is specified first by bit size, that how many levels I want, and the range, the input voltage level. For example, if my quantizer is 0 to 3.3 volts and it is a 2-bit quantizer or 2-bit ADC, that means it can have 4 values: 0, 1, 2 and 3, or 0, 0, 0, 1, 1, 0 and 1, 1. So, it will divide this range 0 to 3.3 in 4 levels, and each will be assigned one value, like 0 to this value, this amplitude will be assigned say a value this, then this is assigned this, something like this. Now, this is one way of mapping. It is not necessary that it has to be mapped always in this manner. And final step is encoding, because you get a quantized value which is one of these levels, that has to be finally sent as a sequence of bits, that is this n bit. So, when you want to buy an ADC, you have to give these 3 specifications. One is the sampling rate, second is the bit size, and third is the input voltage level. So, here we can see that we have 4 bits. So, it can represent anything from 0 to 15, 16 possible levels, like 0, 0, 0, 0 to 1, 1, 1, 1. Let us take an example to make this clear. So, say I have a signal which after sampling I get these values 1, 2, 3, 4, 5 and 6. Very well. So, let us say this ADC is a 3-bit ADC, which means that we have 8 levels, 2 to the power 3. And if the voltage range is say 0 to 5 volts, so what will be done? So, in the quantization we have to divide the range. So, what should be the range? The range is V max minus V min, which means this 0 to 5 and 2 power n. N here is the number of bits, which is 3. So, 2 power 3 is 8, and this is the value. This can be also called the resolution of quantization or the step size. Now, these are the signal values which I had said, these values. So, if you see now, if I say this is my range from 0 to 5 and I have divided into how many? 8, right? 8. So, anything between this, so 0.625 was the resolution. So, anything within this may be mapped to a value 0, like this is mapped to 0. So, this will be mapped to 5, this will be mapped to this will be mapped to this. So, total I can have 8 values. If you use a 4-bit quantizer, then it will be 16 possible values. So, more the bits you are using, the finer approximation you are doing to the analog signal. And finally, you know that these values, even if they are quantized, you cannot really put them in the hardware, because these values are stored in the registers, which are basically made up of flip-flops and which can store either a high or a low, on or off. So, here there are 3 bits, say this is my bit 0, bit 1 and bit 2. So, I have to use either of this combination. So, 8 possible combinations are there. So, 5 will be mapped to 1 1 1. Similarly, this will be mapped to 1 1 0 and so on. Now, next coming to memory. So, as I said that when I am discussing with you anything, or when you achieve any new information, it is very difficult to keep in mind or memorize things. Of course, mind is also a memory, but often we tend to write them down. So, whatever you are keeping in mind, this is a kind of a working memory or kind of a RAM, and something which you note down and you want to keep that for a very long time, that is kind of a permanent memory or ROM, non-volatile thing. So, I am not saying that temporary memory which you are recollecting cannot be a long term memory, but often we keep it in a working memory phenomena or a short term memory. Like say if I go to a movie and I need my seat number, so I will remember it just up to watching the movie, and after that I can forget it. So, similarly, memory can be used for program instruction, where the program code, that is the set of instruction, will be saved, and this is typically in the ROM or flash memory, which means permanent. So, I mean the signal processing system will do convolution whatever data is coming. Then input output data, and these are typically variable data, like now the input is different, after 1 hour the input will be different. So, this memory should be typically temporary and stored in memory buffers and queues, and similarly output of the result. So, these are saved in temporary memory, and this temporary memory is often in the form of RAM. You can also store them in some other kind of memory also, which is not totally non-volatile, but that is entirely optional. And then immediate results, to store processing of immediate results, like I say the 2 plus 3 plus 7 plus 17. So, together you may not be able to add all the 4 operations. So, maybe 2 plus 3 you will do first, then the result you will add with 17, something like that. So, that is what the primary and secondary. So, secondary can also be external and internal. Primary is typically internal, but primary can be external as well. External and internal here means that whether this memory is within the microcontroller or DSP, that is register memory, or external means I have an external RAM or ROM, and that external may be again interfaced with the processor, or it can be inbuilt. And that brings the concept of processing units, where we want to do the operations, and these operations are typically set of programs. As I said, this is an advantage of DSP over ASP, that I can just change the program and that changes my signal processing operation. And where do I store the program? So, typically I write the program in a computer and I will transfer it through some cable or some other media to the microcontroller or microprocessor memory, program memory you would say, and that makes things like microprocessor, microcontroller and DSPs, where the main difference is that microprocessor is a chip where you have your major operation or major operating units, like your arithmetic logic unit ALU, then control unit CU, some register, some internal memories, etc. But you need external things like RAM and ROM to work with, and this is typically found in our computers, and you have to interface this, otherwise it will not work. So, good thing is that you can easily change your RAM size depending on the application, but the bad part is that your physical size will be more. But microcontrollers, everything is in the same IC. So, this is microprocessor. And in DSPs there are some specialized hardwares like barrel shifters, MAC hardware, which are very dedicated for signal processing tasks. And finally, we have the FPGA or field programmable gate array. Now, this is a different concept altogether, because in this, by changing the filter, you are just changing the code. That means the content of the registers of your program memory are just changing. So, you write a separate code, it will work as a separate filter. But in field programmable gate array or FPGAs, the altogether hardware connections are changed when you reprogram it. So, you have to use some HDL or hardware description language to code it into the FPGA, and altogether the hardware connections are changed for this FPGA, and that is why it is called field programmable. But the architectures of these things will be same, only the content of the program memory will change. So, here we are more interested to learn about the signal processors, DSPs. So, like as the name suggests, these are specialized and customized for signal processing applications. And there are three things which are taken into account for designing DSPs. First is real time processing, which means that it should work within real time constraint. Like say for example, you are shooting a video and say your audio and video are not synced, that will destroy your purpose. So, that is real time processing constraint should be there, it should work within the time. Or say you are clicking a photo and of a bird which is sitting, and the moment the capture is done, the bird had flew away, so your purpose is gone. Then high throughput, that means it should execute maximum number of instructions, maybe in parallel if possible, wherever possible do it in parallel. And low latency, latency is basically the difference in time where you give the command to do and actually start doing it. So, that is the main difference, that throughput means the rate at which the data is processed. For example, so if a processor can execute 1 million instructions per second, so its throughput is 1 MIPS. Whereas latency is the total delay to start an operation from the command is sent. For example, say I want to load data, so I send the command load. So, this command is issued say at this interval at t equals to t naught, this command is sent to load the data, and it starts loading at t1, starts loading. So, this difference in time t1 minus t2 is my latency. It is like somebody is commanding me to do the job, and the moment I start doing it, that gap, understanding that thing is latency, and that involves lot of things like traveling path and delay in decoding, etc. So, what are the techniques to enhance the computational throughput? So, throughput should be high and latency should be low. So, there are some specialized modifications in a digital signal processors. Now, these are often coming to microcontrollers as well, and these are, first is a dedicated multiplier, which is a specialized hardware for fast multiplications. Then split ALUs, like 2 or more ALUs work in simultaneous fashion. Another thing is Harvard architecture. Now, this is an architecture where we have the data memory and the program memory separate. So, separate memory for instructions and data. And then parallelism. Parallelism means simultaneously executing multiple operations. Another thing is pipelining, which I discussed, that overlapping instruction execution with stages. And then there is also something called a barrel shifter. A barrel shifter is like a circular shifter which can shift not only a single bit but multiple bits in one clock cycle. So, let us understand what are these, but before, these are some examples of real world DSPs. So, this is the Texas Instrument TMS 320 series, then the analog devices ADSP series, then NXP Freescale DSPs and Qualcomm Hexagon DSPs. So, what is the Harvard architecture? So, in Harvard architecture, as I said, that the program memory and the data memory are separate. Like, what is the program memory? Program memory means a set of instructions like move this, then call this, load this, add this. So, these instructions are kept in registers, and that is in the program memory where you dump the code. And data is where you get the data, like data can be coming from sensors, or data can be generated like random number generated. So, this is data memory. So, Harvard architecture is like you have separate buses. So, separate data and address bus, even control buses are also separate, but I have seen mostly they are referred to data and address bus, and this is the main processing unit, the ALU and the control unit. Whereas in von Neumann, which is in our PCs, are having single data bus and address bus. Also, you see that this data bus is bidirectional, that means data can come and go from the processor to the peripheral, whereas address bus is just from the processor, it is not to and fro. It is like, say, you have a big cupboard and only one shelf, and you keep your jeans and shirts in the same rack. So, that is your von Neumann, and it may be difficult or slower to access. But in Harvard, since they are separate shelves, so you can easily access them, and you can access them in parallel, like simultaneously. So, these are the summary of the differences. Like in von Neumann, you have single memory that is shared, and you have separate memories in Harvard architecture. So, the data and instruction path in von Neumann is same bus, and Harvard there are separate buses for parallel access. So, von Neumann can be slower because of the shared bus, whereas Harvard is faster, and von Neumann naturally is simpler and less complex, but Harvard is more complex in design. So, thank you so much, we will meet again.